Okay, we're going to talk about graphing polynomial functions and rational functions. Just do a few problems, do one problem per video here. So the first problem, this is a polynomial, says p of x is negative 3x cubed minus 7x squared plus 2x plus 8. And what we're going to do is answer a series of questions, get that, and with that information, the answers to those questions, we're going to put that on the graph, and then we're going to use a calculator to kind of get a better idea of exactly what's happening here. So for this one, anytime you are trying to graph a polynomial, it's very helpful to have it in factored form, because that will let you find the x-intercepts if there are any. So for this polynomial p of x, you have a couple options for how to go about factoring this. Really, the easiest way would be to plug it into your calculator, find where the zeros were, and then work backwards to get the factored form. But like this is showing that this is doable by hand. I'm trying to show you that this is doable by hand. So here's how we would do that. If you look at the leading coefficient and the constant, you can do the rational zeros theorem here. The rational zeros theorem states that if there are rational zeros, that those rational zeros has to be a rational expression that's a function, a rational expression that is a factor of the constant divided by a factor of the leading coefficient. So the factors of the constant are 1, 2, 4, 8. The factors of the leading coefficient are 1 and 3. And if we wanted to list all the possible rational roots, rational zeros, they would be 1, 1/3, 2, 2/3, 4, 4/3, 8, and 8/3. We've been over how to narrow this list down and eventually find a rational zero from this list. I will save some time because I already know that one of the rational zeros, the one I would probably find first if I were to attempt this, is negative 2. So if I plug negative 2 in, I'm going to do a division, so I'm essentially factoring this. Negative 3, negative 7, 2, and 8. So if we do this, we get negative 3, 6, negative 1, 2, 4, and negative 8, and 0. So that leaves us with a polynomial that's negative 3x squared minus x plus 4. And then this will further factor to negative 3x minus 4 and x minus 1. Yep. And we can then move all this information back up to the top, because this would be factored if x minus 2, if negative 2 was a 0, then x plus 2 is a factor. So it's that times that times that. I'm actually going to factor the negative 1 out of this one, and when I write it, so this is going to be negative 1 times x plus 2 times 3x plus 4 times x minus 1. So we can so using this, like if we set this equal to 0, that's when we would find the x-intercepts. So we use the zero product property here to find the x-intercepts. They are at negative 2, negative 3/4, and positive 1. The y-intercept occurs when you plug in 0 for x, so it would be y is equal to negative 1 times 0 plus 2 times 0 plus 4 times 0 minus 1. So it's going to be 8 times negative 1 times negative 1, so it's going to be y equals 8. There's a y-intercept at 8. And the end behavior, because we can see that this is an odd degree polynomial with a negative leading coefficient, it's going to do something like this. Okay, we know that. So just by knowing the degree of the polynomial and whether the leading coefficient is positive or negative, we can state the end behavior. And I'm going to do that in limit notation. So what that means is I can say that the limit of the function p of x as x approaches a really, really, really big positive value, like infinity, is going to be negative infinity. Like this would be plugging in really big positive values. This is going down forever. The other end behavior would be that the limit of p of x as x is getting really big negative numbers is going to be positive infinity. Really big negative numbers would be off that way, so it's going to be going up forever that way. Now let's transfer some of these points to the graph. So we can put the x-intercepts. There's one at -2. There's one at -3/4, which is like about right there. There is one at 1. And at this point, we could do a fairly good job of sketching this in. But what I want to do is utilize a graphing utility, and I'm going to show you how to do this on your calculator to get some more precise points, specifically the turning point. So like how high up does this part go and how far down does this part go? Okay, so what you're going to do on your calculator is go to y equals, and we're going to type in the function. So I already have it typed in here, and if we hit graph, you'll see that that's the graph. That's what the graph should look like here. And what we want to do is find the coordinates of this point here and this point here. So we are going to do second calc, and we're going to find a minimum. That will let us find that bottom spot. So it's asking the question to the left. I want to look to the left of of the lower of the minimum, so that's to the left of it. Hit enter, then I'm going to hit over to go to the right, and now it's going to look for the lowest point between these two lines. So I hit enter again, and it's going to give me that coordinate right there. So I'm going to write that coordinate down. Well, I'm going to take a note of that coordinate, and I'm going to put it at it's about -1.68 and -8.9. So -1.68 and -8.9, somewhere right. Oops, sorry. Somewhere about right there. Okay, then I want to find this top point here. I want to find right there. So I'm going to go second calc again, and I'm going to look for a maximum. I'm going to use the calculator to find a point definitely on the left of the maximum. That's there. And I find definitely on the right of the maximum there. Now look in between, somewhere right in that area. That coordinate point is it's 0.131 and 8.13. So 0.131, which is right by the x-axis, the y-axis, and then up past 8. So 1, 2, 3, 4, 5, 6, 7, 8. So we're like right in this area. Okay, and then that's all I need the calculator for. So now you can do a pretty good job of sketching these graphs. So if this one came up way up here, came down, went through that x-intercept, hit that point, through that x-intercept, came up. That's not a very good job of me graphing this, but it's hard to do on this computer. Down like that. And we knew that the coordinate points, this coordinate point here, this was 0.132, and this was 8.35, and this point here, was -1.68, and this point here was -0.89. So what that would then let us do if we wanted to, and we do, because I'm doing this, and I want you guys to be able to do this, would be to answer a couple of other questions. Just deleted some of the end behavior there, but that's okay. I want you to be able to also answer questions like, when is f of x, or I'm sorry, this is p of x, when is p of x decreasing? When p of x is decreasing when it's going down. It's going down from, so if I look at like if I do like a highlighter, this area here is all going down until it gets to this bottom part right there. And then it stops going down, starts going up, and then it picks up going down from here and then back down. So what we want to do is write that in interval notation. And we can do that now that we have the x coordinates of those two turning points. So it's going down from, sounds going real slow here. It's going down from negative infinity, to what is this? And it's rough. Computer's going really slow. From negative infinity to negative 1.68. Union from 0.132 to positive infinity. Notice it's not inclusive of either the negative 1.68 or the 0.132. Sorry, the handwriting is so bad there. I was literally could not see what I was writing because it's going so slow. All right, so you could also do the same thing for when it's increasing. You can use it's a useful skill to have to find those turning points on your calculator. Okay.